for evaluation of transmissivity and storage coefficient in leaky aquifer. It is for leaky aquifer. So the very first question is, what is leaky aquifer? How you define the leaky aquifer? This is the very first question which I would like to ask. Nazir, do you know what leaky aquifer is?
Yes, sir. Assalamu
What is
alaikum, sir.
Valencia? What is leaky aquifer? How you define the leaky aquifer?
सर any portion where it is, वो पोर्शन सर जहाँ पे हमारा एक्वीफर प्रेजेंट हो या उसके ऊपर कोई भी एक्विटार जहाँ से वाटर हम विड्रा कर सकते हैं सर.
Okay. Okay. So it is overlain or underlain by a semi-pervious layer that is aquitar. A
Yes, sir.
leaky aquifer is one which is either overlain or underlain by a semi-pervious layer which has porosity but permeability is relatively low as compared to aquifer. So in case of leaky aquifer, what we think that there is no horizontal flow, but there will be a vertical flow when there we try to pump the aquifer, which is lying below the semi-pervious layer. So, what will be the difference between confined aquifer and unconfined, semi-confined aquifer is that in case of semi-confined aquifer, the aquifer is either overlain or underlain by a semi-pervious layer. Whereas in case of confined aquifer, there will be impervious layer at its top and at its bottom. So aquifer will be in between two impervious layer. So in case of confined aquifer, the mechanism of releasing water is compression of geologic formation and expansion of the pore fluid and expansion of the pore fluid. Obviously, when the formation will compress, so the fluid which is contained in the pore that will expand. So this is the mechanism of releasing. So confined aquifer, either it is in India or somewhere else, their behavior will be the same. Their behavior will be the same that as we pump the well in confined aquifer, so there will be a drop in water level which will be directly proportional to time. As the pumping increases, so does the drawdown. This is what the behavior of confined aquifer is, that drawdown will increase with time. But in case of semi-confined aquifer, what happens when we are pumping for a certain period of time, the aquifer will behave like a confined aquifer. First initial time period, the aquifer will behave like a confined aquifer, but as time proceeds, the water which is contained in the agutar will start migrating downwards vertically into the main aquifer. So the contribution will start coming from the aquitard which is containing water because of leakage. So that is why this particular aquifer is called as leaky aquifer. When the leakage contribution starts, so there will be flattening in the curve. Time versus drawdown curve will getting flattened. There will be flattening in the curve because we are getting an extra recharge from the semi pervious layer. So the nature of this leakage factor will be different for different formation. So for this particular method, Walton has suggested solution for evaluation of aquifer parameter. Now I'll come to the topic. Here I will show you what it is. So this is a diagram which explains the pumping from a leaky aquifer. Okay, I'll explain to you the first diagram, then I'll go to the written part. This is semi-confined or leaky aquifer. Above it, there is a acutard. There is acutard. What acutard means? That it is porous but relatively less permeable as compared to aquifer. So what we consider that in such formation there is one second, somebody want to join. Yeah, so this is acutard which is containing water, and we consider here that there is no horizontal flow, but when we start pumping this aquifer, so the water which is contained here that will start migrating downwards. And how much this will migrate? Above this there is unconfined aquifer, above this acutard there is unconfined aquifer. For unconfined aquifer we have water table, and for this we have piezometric surface, and which is being lowered because we are pumping it at a discharge tube. So how much vertical leakage is taking place? That will be directly proportional to the difference between this drawdown curve of piezometric surface and water table. Water table will remain fixed. What we are not pumping this unconfined aquifer, we are pumping leaky aquifer. This part is only screened. So the water which we are tapping is from this particular aquifer. So the water table will remain fixed. What will be changing? The piezometric surface will be changing. So how much leakage will be taking place? That is directly proportional to difference between piezometric surface, lowering of piezometric surface, and water table. So this particular diagram illustrates the condition of pumping in a leaky aquifer. This Q here designate the discharge, at what discharge, constant discharge we are pumping. This S designate difference between piezometric surface during the pumping and water table. Water table will remain fixed, and how much leakage will be taking place, that designate to the difference between this and this. And this is R. R means radial distance. So if your some observation wells are here, so this particular distance is R. Okay, now I will be coming to the some portion which I have written here. So when a leaky aquifer is, as shown in figure, is pumped, water withdrawn both from aquifer and from saturated portion of overlying aquitard or semi-pervious layer. I have explained to you this. Lowering of piezometric head in the aquifer by pumping creates a hydraulic gradient within the aquitard. Consequently, groundwater migrates vertically downward into the aquifer. I have explained the quantity of water moving downward is proportional to difference between water table and piezometric head. Steady state is possible to well in a leaky aquifer because of recharge through semi-pervious layer. So I'll discuss. Last point. This I have explained to you. The second last point I have already explained to you. The quantity of water moving downward is proportional to difference between water table and piezometric head. This I have already explained to you. This water table will remain fixed because we are tapping this particular aquifer. We are not tapping this one. So if we are pumping this, so water table will not be lowered. Piezometric surface of this particular aquifer will be lower. As pumping proceeds, the drawdown curve expands. As pumping proceeds, drawdown curve expands. So how much migration of water is taking place from here is directly proportional to the difference between these two. Another particular point, the last point which is written, is a steady state will be achieved. When steady state will be achieved, steady state is possible when the leakage factor becomes equal to the quantity which we are pumping. The volume of water which we are pumping is compensated by this vertical leakage. Then equilibrium condition is possible or steady state condition is possible. For steady state conditions, there is a different way of analyzing the data, but here I am talking about the transient state. So what Walton has developed, he has developed equation for non-equilibrium condition, and for non-equilibrium equation condition in semi-confined aquifer, the equation which he has given is S is equal to Q upon 4 pi T WU R by B. This is the equation which he has given for leaky aquifer. This S is drawdown, Q is discharge, T is transmissivity, WU is well function. WU is a well function. So up to here, if I just cover this part, up to here this equation is Thais equation. What addition he has done? He has done introduce a term that is R by B. That is R by B. So what is this B? This B is a leakage factor. This B is leakage factor. And this leakage factor is variable for different aquitard. It is not constant. It depends on the geological characteristic of the formation. So this leakage factor is different for different leaky aquifer. And of course, this R is already defined. So what this B is? B is leakage factor. And then about U is equal to R square S 4TT, the same as in case of confined aquifer. How we estimate the quantity R by B, how it is estimated. So R by B equals R T upon K dash over B dash. This is K dash over B dash. K dash is permeability of hydraulic conductivity of this acutard. K dash is hydraulic conductivity of acutard and B dash is thickness of acutard. So hydraulic conductivity of acutard will vary in different leaky aquifers, and the thickness is also not constant, it will be variable. So the aquifer in question where we are conducting the pumping test, we have to think of the what hydraulic conductivity of acutard, that is represented by K dash, and the thickness of acutard, that is represented by B dash. So this R by B equals R over T upon K dash over B dash. So this is what the R by B is given by. So what so this is what the Walton equation is. Now, where T is transmissivity of the aquifer, K dash is the vertical hydraulic conductivity of aquifer, B dash is thickness of saturated semi-pervious layer. Same thing it is explained here. What I have not said was T, that is transmissivity of the main aquifer. And this K dash is a hydraulic conductivity of aquifer, B dash is thickness of aquifer. Okay. Then in case of Thie's equation, it can be noted that equation 1 has the form of Thie's equation. What that means, I have said that if I cover this, so this equation has a form of, if I cover this R by B, then this equation will be very similar to Thie's method which he has developed. Okay, why it is, what is extra here, that is explained here, that for confined aquifer, this K dash tend to be 0. If your aquifer is confined, so we say it has 0 permeability. It has the layer which is lying above and below the confined aquifer, that will have 0 hydraulic conductivity. So this K dash for confined aquifer tends to be 0. If it is 0, then leakage factor will be infinity. Leakage factor will be infinity. So R by B will become 0, thereby reducing this equation to Thie's equation. So this is just what is more he has tried to explain, that in case of confined aquifer, we consider that it is overlain and underlain by impervious layers which have 0 hydraulic conductivity. If the hydraulic conductivity is 0, that means no flow will be taking place. So the leakage factor will also be infinity. So R by B will become 0. So if this condition is there, so it reduces to S is equal to Q upon 4 pi T W. So implying this analogy, Thie's method of solution, Walton prepared a family of type curve for W R by B. So as I said in the beginning, that in case of Walton's method, in case of Walton's method, I've said that because leakage will not be constant for all the aquifer, it will be varying. The leakage factor will be varying. It will not be the same. So one type curve is not possible. One kind of, as in case of confined aquifer, Thais has developed type curve by taking values of W and 1 by U for confined aquifer, and then he has come up with a single master curve that if your aquifer is confined, so this well functions relationship will be like this. But in case of Walton's method, a leaky aquifer, the leakage factor will be variable. It depends on the geological characteristic of the aquitard and what kind of hydraulic conductivity the leaky formation has, and what is its thickness, all those things. So it is variable. So Walton has developed a family of type curve. He has prepared a family of type curve. I will show it to you. This is Walton's curve. This is Walton's curve, and this is W R by B. I'll blow it. So this is Walton's curve. Here it is W R by B, 1 by U. So you see this, there are a number of graphs which is developed by him for all kind of, all possibilities of leaky aquifer, for all possibilities in leaky aquifer. So this is one graph, and here the R by B is 2.5. This is second graph. Here the R by B is 2. Here it is 1.5. Here it is 1. And the last one which I can see here is 0.001. The value of leakage is 0.001. So it varies from 2.5 to 0.001. Now what you have to do? What kind of practice you have to adopt for solving the pumping test data for semi-confined aquifer or for leaky aquifer. We will be conducting the pumping test in the same manner as we do for any aquifer. And how will be conducting? We will have a pumping test here, a pumping well here, which is tapping the leaky aquifer, and above this there is unconfined aquifer. We are not taking the water, involving the water which is contained here in the unconfined aquifer. So this dashed line shows the screen portion of the well. So any water which will be coming to the well is from this particular aquifer. Then we need to have an observation well, which may be drilled here, tapping the same leaky aquifer at distance r. Now we start pumping at a discharge q, and then we measure the change in water level, potentiometric surface in pumping well, as well as observation well, which is located at a distance r. So we'll be measuring first the non-pumping piezometric surface, and then we'll start measuring the pumping water levels at well-defined time intervals. At well-defined time intervals. Then what we do, we'll be subtracting this pumping water level from the non-pumping water level, so we'll obtain the value of drawdown. We'll be able to obtain the value of drawdown. Then once we have this particular data, then we'll be plotting a graph, field data curve, that is time versus drawdown data, time on x-axis and drawdown on the y-axis. And the axes of this your type curve, whatever you have type curve of Walton, should have the similar axes of your data curve, that is your time versus drawdown data. And both these graphs on log scale, so your time drawdown data should also be on the log scale, and the axes of this graph and data curve graph should be same. Like if 1 is here, 10 is here, so your data curve should also have the same axes. Then what you will do, you will superimpose your data curve here onto this graph, and you will have number of dots on your data curve that will be your drawdown at different time intervals. Now you will be keeping these two axes parallel. You will be sliding your data curve onto this one, where it matches with one of these graphs. So you take that as a match point, and you read the value of R by B from here, W from this particular axis, and 1 by U from here. Once you have this, then for that particular match point, you read time and draw down from your data curve for the match point. Your graph may be matching here, your graph may be matching here, your graph may be matching here. So wherever it match with this one of this curve, so that will be your match point, and you will be noting down the value of W and R by B from where it is matching, and 1 by U from where it is matching, and then you will have solution for this particular method, and how we will be getting the solution. Solution you will be getting from these equations. Discharge is known to you. Drawdown you have read it from your data curve. For the match point, W you have noted from the type curve of Walton. R by B you have noted from the type curve of Walton. So you will be able to evaluate the transmissivity of your leaky aquifer. And in then again you will be able to calculate. R is known to us. It is the distance between pumping well and observation well, and S is you have to calculate its storage coefficient. Transmissivity we have calculated already, so we'll put the value. And this T is the time where the your graph has matched. So this is a time you have to put here, and you have to keep the units in the same comparable units you have to choose. So then you put this T and R and value of U, then you will be able to calculate the storage coefficient. So this is how the Walton's method is applied for evaluation of pumping test data for leaky aquifer. This is the method for evaluating the transmissivity of your leaky aquifer, storage coefficient of your leaky aquifer. So here it is same thing what I've written. So for imposing two sheets while keeping coordinates axis parallel, a position is found where most of the points and data fall on the type curve. Selecting any convenient match point, values of W, R by B, 1 by U, S and T are noted. Transmissivity is then found from equation 1, storage coefficient from equation 2. Finally, from the value of R by B belonging to the type curve of best fit, it is possible to calculate K dash over B dash from equation 3, and if B is known from the field condition, K dash can be evaluated. So we can solve this equation as well. This can also be solved. This equation can also be solved by noting down this particular parameter. T we have evaluated. Thickness is known to us by what you call uh, drilling data. Thickness of acutard you can know with the help of drilling data, and R by B we have read from the graph. This R is known to us. Transmissivity we have calculated, so that acutard hydraulic conductivity can be calculated by this particular method. So this is what the Walton's method of solution is, and this is what I plan to talk to you with you today. So this is what, if you have any question or anything, just you raise your question. If you have any question, please ask the question. I have another class of MSc. So if you have any question or any doubt, you just ask the question. Yes, is it okay?
Yes, sir.
Mushir Riaz, Mushir Riaz, Mushir Riaz.
जी सर, अस्सलाम वालेकुम
वालेकुम। मुशीर कुछ समझ में आया क्या?
सर। जी सर।
आप कहाँ से आए हैं?
सर मैं पटना से हूँ।
तो ये समझ में आया जो मैंने आपको पढ़ाया? देखो
जी सर, आया।
ठीक ठीक। खालिद कुछ बोल रहे थे?